Uh, I work with Professor Neerav back in IIT Madras in India. I'm a grad student, and my area of interest would be to develop AI algorithms and applications to be used in the field of drug discovery. And this is the latest work to come out of our group. And yeah, I'll just give a brief introduction about what we've been doing till now. So to start with, I would ask what is drug discovery in general? I would say it's the art of creating new medicines. And the typical drug discovery pipeline goes like this. You are a medicinal chemist, right? You work in a lab or a company and so on. What you have with you is a well-defined protein target as such, okay? And your job as a medicinal chemist is to imagine a molecule that will actually bind to the protein. It can make sure it binds, have the desired effect, and so on. And most of this mainly comes from the intuition of the medicinal chemist through his years of training and or domain knowledge, as I would call it. Okay? This is the more traditional way of doing it. Some statistics on drug discovery as such. Uh, around 9 trillion US dollars is spent on healthcare annually, and bringing a new medicine to market costs over $1 billion. Takes a very long time. It's approximated to be 14 years, and the success rate is very, very low. I would say less than 1%. Okay, the majority of the time is spent in clinical trials and finding the specific protein target. Okay, this is where most of the time is spent. But there are different stages. Once you have a target in mind, you need to come up with new drugs. For that, there is the optimization stage. Then there are your, you know, toxicological studies, your phase one discovery process goes on. And you might say there are thousands of drugs existing. The list of FDA approved drugs goes around 20,000. Why do we need newer ones? Okay. The first use case I can think of is, what if there is a new disease? A very good example of this is the COVID pandemic. Okay, what if something unexpected happens and you need to come up with a drug very quickly? Or another one can be, can we make the existing drugs more effective, more cost efficient, so on. This is another one. The third major reason is, the rising problem of drug resistance. Drug resistance, I would say, a drug is effective for a particular condition, and over time, the same drug doesn't work. How can we overcome it? Uh, that is another problem, and maybe in the near future, it can be used for personalized medicine as such, where each and every individual can have their own custom design drug. Maybe in the future, not right now as such, but yeah, maybe in the future. And the typical approaches used in the drug discovery pipeline, your pharmacophore modeling, where you look at the binding site, see how the interactions are, and a medicinal chemist can design drugs so that it binds to the correct binding site. Or you can have the molecular dynamics simulation, where you can where you can actually see how the binding happens over time, how the protein, how it interacts with the protein, uh, and so on. And then you have your virtual screening case where you already have a library of millions of molecules and you just screen through them very fast. That is what I call virtual screening, and this is the funnel approach where you have your existing molecules, try to filter them with some specific criteria and try to come up with a drug. And then the last one is called scaffold hopping, where if you look at these molecules, the one in colored boxes are, I would say, active substructures. Okay. Once you know active substructures which can bind to your protein pocket, what you can do is try to join these two or four different substructures together and see if it has more enhanced effect than the original molecule. Is what I call scaffold hopping as such. These are your traditional approaches. And why this is not enough? Because the number of synthesizable drug candidates. What I mean by synthesizable is you can have any molecule like this, but if you can't make it in the lab, it's of no use. You actually need to make it in the lab. That is what I call this molecule is synthesizable because it can be made in the lab. Okay? The number of synthesizable drug candidates ranges between 10 to the power 23 to 10 to the power 60. Okay? This is like very huge. Okay? And all these traditional approaches rely on the knowledge of limited chemical space. We've only seen the largest curated database that we have right now is the GDB database having around 166 billion compounds. That's just a very tiny fraction compared to 10 to the power 60. This is what we've seen till now, and still there's a lot more to be explored. Okay, and how do we do this? I think AI is the way forward. It has achieved, it is currently the state of the art method across various domains like vision, text, etc. I mean, if you know ChatGPT, it is everywhere. Everyone is using it. Uh, AI is the principle behind it, and yeah, you can see how much impact it has had on many domains, and it can also have the same effect in drug discovery as well. Uh, what I've been talking till now is not like a distant dream, I would say. Uh, there have been AI designed drugs as such. It was first in 2020. Accenture actually came up with the first ever AI designed drug, which was for OCD or obsessive compulsive disorder. Then came your AlphaFold movement, where it can predict protein structures within seconds. And then in 2022, there was a complete pipeline where the AI discovered the protein target as well as the molecule itself for a very rare condition called idiopathic pulmonary fibrosis. And in 2023, we've been seeing de novo antibodies being, small protein snippets completely using generative AI, and uh, the drug designed by In Silico Medicine is currently in phase 2 trials right now. Okay? So AI has helped a lot. It has cut down time, cost, and people have been actually using it to design drugs. If you look at AI in drug discovery, there are, these are just three that I've shown right now, but it's been used in other subfields of drug discovery, I would say. You have your molecule generation where you need to come up with new molecules. Then there is your property prediction where without doing any experiments can we predict how effective the molecule is. And then there's also your synthesis pathway design where if you need to make this molecule, you need to design these steps. Okay. It can't just be, it's not available anywhere in the world right now. So you can't extract it from some plant. You need to synthesize it in the lab as such. Okay. These are some areas where AI is used for. And the one that I'm going to focus on right now is the de novo molecule generation case, where you need to come up with newer and newer molecules. Okay. But for that case, if you want to use AI, the performance mainly depends on the input representation. What I mean by representation, how do computers actually read it? Okay? You can have your graph representation where your atoms are your nodes, the bonds are your edges. You can have a text-based representation, or what we call a line notation. This is your smiles line notation as such, where as you can see, each substring corresponds with substructure in a molecule. Okay? Or you can have a 3D molecule as this, okay, where you actually have, sort of like a 3D point cloud of your molecules. So this is the choice that we have with us. And what do we do? Which one do we choose? We went ahead and chose the text-based representation. Why so? Because these text-based representations of molecules allow for efficient exploration of the largest chemical space. Okay, what I mean by exploration of the largest chemical space, because ChatGPT and Gemini, these are like huge models trained on huge amount of text data and has shown incredible performance for many downstream tasks. And we were thinking,
Roshan,
yeah,
Roshan,
yeah,
a question here.
yeah,
On molecular representation, I
yeah,
want to take the context as if we are inputting it as an input to the model,
yeah,
we probably, the most common, at least I see, the smile molecules, which I think is the one in the middle.
yes.
Um, I'm aware of the other representations, but I think I'll take this opportunity to ask if we can represent the structure like not the smile string, how do we like represent it and becomes an input to the model away from the smiles input? I hope the question is clear.
So you mean how the conversion from this to this happens?
Yes, if it, okay, like what I'm asking is if it's not a smiles input, what
Mhm.
is the other option? Could it be a structure input, and how does that work?
Yeah, okay. The other input is, as I talked about, it's a graph
Yeah.
where these atoms are your nodes, these bonds are your edges. Okay, and you might think this is more of a natural way to represent your molecules as input because this is how it's connected in real life too. But the architectures for GNNs or graph neural networks right now are not scalable to billions of data points. That's the main issue there. Or you can have your structure, your 3D structure. What you can do is you can have the same graph input and you can augment it with the 3D coordinates. So you have the 2D, you have the 3D, and you have the sort of like one-dimensional representation. Is this clear or?
Yeah, I think that makes sense actually. Yeah, as so in the context of using GNNs,
Mhm.
so you have to express the molecule as a graph, like nodes
Yes.
and
Yes.
edges. Okay, that makes sense. So do we have another option of this third option being like sort of a structure?
Yeah, this is the structure-based one. Basically, you augment your existing graph by adding in 3D coordinates to the graph as positions.
Okay. Oh, oh,
Yeah,
yeah.
you just add extra information to each of these nodes saying that this atom is in this position.
I see. I
and
see. I see.
that will be your input to your 3D based graphical networks.
Thank you.
Yeah, but then both the 2D and the 3D approach are not scalable, and for the case of graphs, we are limited by the architecture right now because transformers are scalable for billions of data points as demonstrated by ChatGPT and everything. But the problem with using 3D structures is you only have around 400,000, experimentally determined conformers with you. Okay. You don't have a lot of data for the 3D case. But in the case of 2D or 1D, you have billions of molecules, as I talked about the GDP database before. So we really want something that's scalable that can allow for more exploration of the chemical space. And we also don't want the model to, keep producing the same output again and again. We want them to be more diverse. And previous research has shown that, these molecular large language models actually do all these things. Okay? But when we thought we'll sort of like build a foundation model for molecules using the string or text-based representation, there was no consensus on string representation, what's the input tokenization, and whether there are any scaling laws for these models. Okay. This is the problem that we face, and we thought we'll investigate this a bit more. Okay. And this is sort of like this is our experimental setup, I would say. You have around, we took molecules from the Zinc 22 database. It currently has around 70 billion molecules, but we wanted to do a very controlled study exploring multiple factors in molecular language models. So we were sort of a bit constrained. We can't retrain on all the 70 billion molecules right now. So we took a subset of 1.5 billion molecules, but we again ensured that these are diverse enough. What we did is typical, deduplication, conversion to different text input. And okay, why do we need different text-based input? Just like how we have different languages that we communicate in, molecules also have different languages, okay, that they can be represented in. So you have smiles, you have selfies, you have deep smiles, you have safe. Each one is different. Each one they have their own advantages and disadvantages, I would say. Because let's take the case of smiles. Okay. If you look at a smile string here, if you just, remove this one, okay, you can't convert this back. Okay. This text to structure conversion is not possible just because you remove something in the middle. Okay. But in the case of selfies, if you remove a token, let's say branch one, or or okay, if we don't talk about removing a token here, we can just think about reshuffling it. Okay, reshuffling the order of these individual letters, the smile string, the conversion doesn't work. But in the case of selfies, if you do rearrange these individual tokens, entities, or atoms as such, you can still get back the original structure like this. Okay. Uh, and safe also sort of like has a similar syntax to smiles, but then here you can do other generative tasks like fragment constant generation and so on that maybe I'll explain a bit later. So each one has their own advantage and disadvantage, and we wanted to see which one actually is the best. Okay, here's one thing. And if you look at input tokenization choices, you have atom-wise and byte encoding. Atom-wise, if I talk about tokenization, okay, let's say you want to represent a molecule as an input to your language model. Do we ask the language model to see it as a bunch of atoms or a bunch of substructures? Okay. Do you want the model to see this whole substructure and this substructure, or just like individual atoms? We also wanted to investigate this, whether, I mean, which approach is better. We thought atom-wise would be the most sensible one because it represents atoms that are, the most fundamental. Molecules are composed of atoms, and we thought, okay, this might work best, but that was not the case, which I'll explain later. This is your typical pre-training pipeline, um, similar to how existing language models are trained. We used a llama model with flash attention, and what we aim here is that the model learns chemical validity and syntax. It learns the grammar of smiles, safe, selfies, deep smiles, and so on. Okay. And what you get ultimately is unconstrained molecular generation along the learned manifold. Okay, let me explain this concept with this diagram here. The one, the darker regions that you see here are regions having more desirable properties. Okay. If you look at it, let's say you want to generate a molecule that's more likely to become a drug. You want the model to generate more molecules in this region. Okay. But in the case of pre-training, it doesn't know, it doesn't have any context, and it can generate molecules anywhere in this space. Okay. So that's the problem with just pre-training alone. It will only be able to generate molecules, but not generate molecules with a given context. Okay. This is the first phase, pre-training. We wanted to check whether the molecule is able to produce different molecules. And these are these are some set of evaluation metrics that you care about after pre-training your model. The first one is validity, whether the generated structures are actually valid, chemically valid. That is one thing. The
Uh,
next
Roshan,
important, yeah,
yes, I have a question on the previous
yes,
slide also.
yeah,
When you say the model generates a molecule without context,
yes.
one, does that mean a way like a lot of deviation from the actual anticipated molecule? But also, can it be related to maybe the lack of in context learning? But maybe also with that, you can add on the context of continual learning in that sense. Like, do we lacking that? I'm just asking. Yes.
Okay. What I mean by context here is, see, you see this sort of like region here, right? This is for only one specific property that you're interested in. The region won't be same for different properties. So as I said, it changes according to the context. Okay. And just the, and if you look at models like ChatGPT and Gemini, if you just look at the pre-training phase, pre-trained models, okay, if you type in a prompt, it won't generate a very coherent answer. What you need to do is some sort of fine tuning. I mean, in context learning is one of those, but there is an additional fine tuning phase where you sort of like give the model context saying, for this prompt, this will be your answer. For this prompt, this will be your answer. Some examples for the model to learn. And that's your fine tuning phase. The same thing exists here. Okay. But the context here is a bit different because you can't just type in saying, you know, give me a molecule with high drug likeness. You can't do it like that for these kind of models.
Mhm. Yeah.
And you need sort of like different approaches.
Okay.
Okay. So this is one thing, and evaluation wise, validity is one. Novelty, whether the model actually generates molecules that are not present in the training set, because you want newer and newer molecules, not the same old ones again and again. This is one thing. Then you have a bunch of metrics like FCD, SNN, scaffold and fragment similarity. FCD captures biological properties of molecules. Ascending scaffold and fragments see how the generated molecules are different. Is it able to produce new substructures? Okay, not keep, and it does, and make sure it does not keep generating the same substructures again and again. This is one thing. And this is, if you look at it, okay, these are the NovoMolGen set of models that we have pre-trained. You have different model sizes, different tokenization types, different molecule representations. As you can see, our novelty is like way higher when compared with the existing baseline. Okay, all the models, all the the family of NovoMolGen models, the novelty is around 98%. Most of the molecules produced are actually valid. You capture the better biological properties and also keep producing different newer and newer substructures. So this was like a very significant milestone that we achieved in the pre-training phase. The only pre-training improvement that we did was use a newer architecture, use all the latest language modeling tricks like RMS norm, Swigglue activation, rope embeddings, and also to speed up training, we also use flash retention. So all the latest architectural innovations were there in our pre-training phase. And that's what led to a very significant improvement in all the pre-training metrics. Some generated samples that we have, these are all molecules that I can say that people have not seen before. These are not present in Zinc 22 as such. They have good synthesizability. Synthesizability meaning these can actually be made in the lab, and the drug likeness is very high. These are more likely to become a drug. Okay. Any questions till now?
Yes,
Because
there is
yeah.
one where someone is asking, do you advise imputing missing data? I think in the case of training.
Mhm. Okay.
Yeah.
We don't have any labels as such because it's the pre-training phase. It's sort of like self-supervised learning. You don't have any missing data here as such.
Yeah, it makes sense because you have molecules and
Yeah, we don't have any properties associated with them. So you don't
yeah,
have any missing data.
makes sense.
Yeah. Anything else?
No, I think so far,
Okay.
yes.
Okay. Okay. And if you look at these molecules, uh, I mean, you can say that these are just random generations from the molecule. But at least it's good that these molecules are valid, but we won't be satisfied with random generations. We actually need to construct a use case for these models. And this is where the fine-tuning phase comes. Okay? Because these pre-trained generative models, they don't know what molecular properties are. Okay. But what you need to do is sort of like steer the exploration towards these peaks where 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 you can produce molecules that have really good properties. And this is what we sort of do, where you have the grow step and the improve step. Meaning, in the grow step, you ask the model to generate random molecules. Okay? Among the generated random molecules, you sort of filter them according to whatever criteria you want. The criteria can be drug likeness, synthesizability, or better binding to a protein target, and so on and so on. So you have many properties that you can filter for. Let's say at the initial growth step, the model randomly generates 50 molecules. You sort of like do a scoring for these 50 molecules and rank them based on the property. Then what you do is take the top 10, feed it back to the model again, keep doing this. So this is sort of your explore and exploit situation going on. You don't restrict the model to a very few high scoring molecules. You also ask the model to explore more and more of the chemical space. This is sort of like just from our fine tuning pipeline, but there are like more technical details. For that, I would refer you to our paper. But yeah, this is the basic idea here. And we want to test these for different use cases. Okay. I mean, the chart is too dense, I guess, because there is a lot of information going on, but I'll try to deconstruct what's going on here. So in the bottom two, you can see baselines with which we compare our models to. Here you have different tasks. Okay, if you look at the albuterol similarity task, in this task, you want our model to generate more and more similar molecules to albuterol. This is one thing. Then you have amlodipine NPO. What we want is we want a newer drug that's different from amlodipine, but also has the same properties as amlodipine. You have DRD2, where you want to generate molecules that binds tightly with a specific protein target. So you have like multiple different tasks here. Okay? And this sort of like covers most of the tasks in generative ligand discovery as such. Okay? This is sort of like a very broad enough evaluation that we are doing here. Make sure the model is tested for every use case. And as you can see, the NovoMolGen smiles, the 300 million parameter one with the BP tokenization actually achieve the best score. But there is not like much difference between all these models. Just for the benchmark case, you can say that this one achieves the best performance. But ultimately, we came to the conclusion that, okay, the BP set of models are working way better than the atomized models. And if you keep scaling from 32 million to 300 million, the jump is not that significant enough that you would hope to see. So what we sort of like thought here is maybe scaling doesn't work for the case of molecular language models. But if you think about Gemini, ChatGPT, and so on, they have like billions of parameters. Okay. And if you look at smaller language models, they don't work as well as the bigger language models. And this is quite contradicting to what we see in the NLP domain as such. This is one sort of like evaluation. Then we actually wanted to test it across different protein targets as such. These are the 5 different targets. Each one, so there are some proteins that are implicated in cancer. So what I mean by this is, if you design a drug for this specific protein, you can sort of stop the progression of cancer. So this is like a more sort of like grounded in reality, where you are designing drugs for different use cases like cancer, blood clotting, neurotransmitter regulation, and so on. And what we have in this table is your docking scores and hit ratios. I mean, you can think of docking score because the lower it is, the better it is. And these are our set of models. The ones in blue are the best performing ones. And if you can see these scores, ours are way better than existing baselines. And we also have significantly better or higher hit ratios. Docking score is basically quantifies how tightly your molecule binds to the target. If it's more tight, it's better. So minus 14 is more, you have a stronger binding than minus 12.95. That is how you interpret the docking score. Hit ratio meaning, let's say you generate 100 molecules, okay, and you need among these 100, if my hit ratio is 90%, 90 of my molecules are actually binding to the target. If it's 40%, only 40 molecules are binding. So we have higher hit ratios, higher docking scores. This was kind of another good milestone that we had in our paper. But yes, we developed a new family of foundation models for de novo molecule generation. These are some molecules that we had from these models. Okay. These are quite good, I would say. I mean, we haven't looked at it more thoroughly, but based on the docking scores, they seem to be better. And one more thing we wanted to investigate is the training dynamics. Typically, in the case of language models, more data you have, better your performance will be. But in our case, as you can see, no, there's no difference. Just after the initial checkpoint, there's no improvement. And also, if you look at all the model sizes, there's not significant improvement either. And this was like a very major counterintuitive result that we had that was not in the literature before. So what we conclude from this is ours is the state-of-the-art generative model, de novo molecule generation. Models perform comparably as size increases because uh, based on this study, we can say that scaling is not necessary to learn the molecular language. And ultimately, from our study, we recommend that use the SMILES representation DPE tokenization because atom-wise and other representations don't seem to work that well. And pre-training on more and more molecules does not yield good returns. Okay. And this is the de novo molecule generation case that I talked about, but it can do other tasks like scaffold decoration, scaffold morphing, electrosynthesis, and so on. Maybe if you need a bit of a primer on these, de novo molecule generation meaning you create a molecule out of no assumptions here. Okay, you don't have a prompt as such. But if you look at these, yes, I'll just give this part as input to my molecule and ask the model to complete this whole structure. These are called fragment constraint generation tasks that we are working on right now. Yeah, thank you. Uh, I think this was a bit fast, I
Thank you.
guess, very short, but if you have any questions, I'd be happy to
Thank
answer.
you, Roshan. There is one here.
Yeah.
Someone was asking, what challenges did you encounter with I think he meant chemically sensible molecules in terms of chemical validity, but I think maybe in terms of also synthesizability.
Okay.
Yeah.
Okay. Uh, so, if I can rephrase the question as such, you mean to say, how did we check for validity and synthesizability? Is that the question?
Yes, like I think here, yeah, what
Okay.
challenges were encountered in,
Okay.
yes.
Okay. The first thing, how we calculate validity and synthesizability is we use a proxy metric here. We don't design these metrics. It has been designed way back in 2004, and we've been using the same metric as till now. What the metric will actually do is take this smile string as input, and it will output a score. Okay, that is your synthesizability. Same for drug likeness, and that is what we basically call an oracle. Give your smiles as input, get your synthesizability, drug likeness, or any property that you can think of as output. We don't do any experiments as such. We just feed it to the metric, it will give you a score. If you want to know how the metric works, I can give a separate explanation for that. But this is the basic thing that we are dealing with. Yes.
Yeah, I think there is a follow-up question.
Yeah.
Is meaning like the nonsensical molecules that don't obey the chemistry principles. I think how they were weeded out. I hope that's what he's trying to
Can you
infer.
repeat it?
Like he's following up with
Mm-hmm.
the non-sensical molecules, like
Oh,
that.
okay. Okay.
Yes, that don't
Okay.
obey the chemistry principles.
Yes. 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 Okay. I get that question. So, validity in this case, meaning, uh, how can if I'm able to convert this string to this structure, okay, I can say the molecule is valid. We don't do any other checks for that case. But if you actually want to say whether a molecule is possible, we calculate the synthesizability score. We call it the SA score. So that gives you an idea whether the molecule is actually possible. It can be made in the lab. Okay. Yeah. If that answers the question, that's what I guess.
I hope.
I have something.
Yeah.
Okay.
Yeah, thank you, Balaj, and thank you, Lukman, for uh, this invitation. Well, I'm actually impressed by the gentleman's presentation, and it's really good. I was actually trying to understand, when you're dealing with some of these molecules, there are those molecules that will really comply and those that will not comply with certain properties within
Yes.
the set principles of the tool that you're using. Yeah, and my quest was, I wanted to really understand one, where did you have or did you encounter the non-sensical molecule? And if you did, uh, how did they respond in terms of validity and all that? Then
Okay.
secondly, if you didn't, could there have been room whereby there are those that were 50-50 in terms of compliance, and where did they really fall in terms of chemical validity of the whole experiment? Thank you.
Okay. Okay. So in the pre-training phase, we can't really constrain the model to generate more. I mean, okay, there is validity in terms of converting the molecule from smiles to the structure, and there is sort of like your chemical validity where a chemist can look at a molecule and say, this is okay, this is possible, this might not be possible. Okay. And this sort of like improve step, the filtering is a major thing that we do here. What we do is once you generate the molecules, you basically filter, remove all these invalid molecules, and just feed the good molecules back to your model again and again. So while doing this, the model will sort of like learn to produce just molecules that are like theoretically possible. It can that are actually, that are sensical. So once you do this filtering and keep feeding the good molecules back to your model again and again, the model sort of like learns to generate only those good molecules that have desired properties.
Okay. So Roshan, is this part of the training process? Like,
Yes, this is part of the fine-tuning process. Yes.
okay.
So it's not just fine-tune, it's filter and fine-tune.
Okay. I don't know whether Gabriel, that answers your question.
Yeah. I get it. He actually answers it very well. And I wanted also to follow up with something.
Sure.
In Torashan, actually, is there a possibility of coming up with a nonsensical molecule intentionally in your experiment to check
Mhm.
whether it can respond based on the tests or whatever the achievement that you want to achieve, and then have a comparison based on that error, intentional error in terms of the molecule formation.
Okay. So what you mean to say is we let the model generate those invalid molecules and sort of like learn from it. Uh, is that what you're asking? Or
I don't know whether when I was talking about the nonsensical molecules,
Mhm.
of course, I was meaning those that do not comply with the
Yes,
principles, the chemical
yes,
principles of the experiment.
yes, yes.
Now, whatever molecules we're using were
Mhm.
molecules designed to fit within the parameters of the experiment, right?
Yes.
Now, in the follow-up experiment, could there be an adjustment to check the balance or of the output in terms of
Mhm.
the non-compliance of the molecule vis-a-vis those molecules that are designed with compliance parameters? Thank
Okay. So if the molecule cannot be translated back to a structure as such, we won't be able to infer any properties for that molecule because it's incomplete as such. We won't be able to get any property information out of that molecule.
you. Oh,
So
thank you. That's okay.
yeah,
I
yeah,
get it now. Thank you.
yes. If the molecule is incomplete, you won't be able to get a score anyway.
Thank you, Roshan and Gabriel. My question is about the tokenization methods, byte pair and atomwise, and
Yes.
I I would say I would be biased to always move with byte pair encoding, but
Hmm.
uh, which ones here performs better, or is there significant like performance between the two in variations?
Uh,
Yes.
okay. Based on our results, I would say there's no significant difference between BPE and atom-wise. Maybe BP is slightly better when compared to atom-wise. I mean, not significant enough for a real-world utility, I would say. But what we recommend is going with the byte pair encoding because with a reduced context length, because we are dealing with substructures, not individual atom tokens. So what happens here is it effectively reduces your context length. So it's more efficient and it can, let's say, given a context length of 64, it can generate a longer molecule compared to atom-wise. So we think about BP in the case of performance-wise, yeah, there's no difference. But if you wanted to be more efficient, yes, go ahead with BP.
All right. I think maybe the final from me would be from Turashan to give us the final takeaway from this work, like that someone should go away with, at least in your view.
Okay. Okay. The final takeaway that I really want to put out there is basically we've been training models, especially in biology and chemistry, where we borrow approaches from other AI fields. Okay. For the same molecule generation uh, sort of like model that we did, we took everything from the natural language processing field, okay, and sort of like adapted it to the chemistry use case that we have here. But what the actual research it should actually be done where we develop architectures that are like have an inductive bias with respect to chemistry and biology. All those principles are sort of like inbuilt into the architecture itself rather than learning from the data as such. That is one thing. And one more thing that I want to put out there is maybe the way we are evaluating these models are sort of like really simple. Maybe yes, you can come up with an AI designed drug with our models, but that might just be due to a random chance rather than the model actually learning anything from these chemistry principles and then outputting really good molecules. So maybe our evaluation should be more sort of like rigorous. And yes, we really need to build architectures that are like more ingrained with chemistry and biology principles rather than borrowing architectures from different fields. So that's my main takeaway here.
Thank you very much, Roshan. And I think that is a direction, but that researchers in this field should
Yes.
look into. And today I saw a paper from NeurIPSI. It is mainly in language processing, where the Google researchers are introducing this concept of nested learning, and they're interrogating the layers within the neural networks, that
Yes.
understanding and propagating knowledge within the layers. And talking about that, like building architectures that are inherently having the knowledge of chemistry in this field. I think that's an interesting take. I want to thank you. Thank you for saving up time and talk to us about this work. But I
Thank you
also
for
want
having me here.
I want to thank Professor Nirav also. Send my regards. And thank you very much. Thank you very much indeed.
Thank you.
All right. So goodbye to Roshan and to everyone on the call. And we meet in our subsequent sessions, which probably will be next year. Bye-bye, everyone.
Thank you. And if you have any questions, you can contact me through email.
All right. Thank you for that lead.
Yeah.
Okay.